Welcome to Wiki Lectures. Coming to the second session of magnetostatics. We have already studied the straight currents. Here we are considering circular currents. It is the current passing through a circular current carrying conductor. So here we are considering a circular element in which is a length R. Here we are going to measure a magnetic field B. So this is a small element that we are considering here with a length dl. So the current element will be ideal. This is the length dl and the current element will be ideal. So from Biot-Savart law, we know that the magnetic field produced by a small current element ideal will be dB is equal to the magnitude will be equal to dB equal to mu 0 I mu 0 by 4 pi into I dl sine theta divided by r square. This is the expression that we are getting from Biot-Savart law. So which is equal to mu 0 by 4 pi into I dl sine theta. What is the theta here? It is the angle which makes ideal with this direction. So this direction will be in this direction, radial direction. So it makes an angle 90-degree with this, as this is in tangential direction. When we are considering a small element, length element here, it will be always tangential to this radius. So this angle will be equal to 90-degree. So I dl sine theta, that is I into dl into sine theta, it's sine 90. Sine 90 is equal to 1. So I dl divided by r square can be written as mu 0 I by 4 pi into dl divided by r square. So here, as you know, this dl is the length element corresponding to a current passing through an angle phi, or just consider a current passing through this direction. Current is passing through this direction. If a current passing through this direction with an angle d phi with this center, with an angle d phi with center, the corresponding length is represented as dl. So it is corresponding to the movement of a current with an angle d phi. It may makes an angle with this center d phi. So how can be represented? Can also be represented as dl can be represented as dl is equal to r d phi. R d phi, because this is the radius r, and this can be considered as an angle d phi, as an angle d phi. So if this is r and this angle is d phi, this will be around equal to arc length. So it is equal to dl is equal to r d theta. So this can also be represented as dB is equal to mu 0 I divided by 4 pi into dl can be represented as r d phi divided by r square. So r d phi divided by r square. Here r and r square gets cancelled. So it will be mu 0 I by 4 pi r into d phi Okay. So b can be represented as b is equal to mu 0 I by 4 pi r. What will be b? B will be this dB is corresponding to this small angle d phi. So b will be corresponding to total element, total phi. So total phi can be represented like this phi. This is the angle phi. How much is the angle it making? Here you can see that from here to here, this much distance is there. So how much angle it makes with the center, that will be equal to phi. So b is equal to mu 0 I by 4 pi r into phi. The angle made by the segment at the center. Phi is the, what is phi? Phi is the angle made by the segment. How much segment we are considering, how much current is passing like that segment at the center, that is phi. Let us consider an example. Here if we are taking an it's a half circle. It's a half circle. If a half circle, we are just consider it as a half circle. So how much is the angle which it makes from here to here, which means it is pi, 180-degree angle is there. So when we are considering this magnetic field B, if current I is passing through here, V will be equal to mu 0 I by 4 pi r into the angle phi, which is equal to mu 0 I by 4 pi r into pi. pi and pi get cancelled, so it is equal to mu 0 I by 4r. Okay, this is the expression. And if it is a full circle, if it is a complete ring which carries a current I, then how much is the current magnetic field which makes at the center here? So it is equal to B is equal to mu 0, again mu 0 I by 4 pi r into the angle phi. So it is equal to mu 0 I by 4 pi r. How much is this angle? 2 pi, total 360 degree. So it is equal to 2 pi. 2 pi and 4 pi get cancelled. Remaining 2 will become mu 0 I by 2r. So remember this equation. This is important. That is how much the magnetic field when a current through a circular ring. It's a circular ring which carries a current I. So from the effect of this complete ring, it will produce a magnetic field at the center, which is equal to mu 0 I by 2r. Okay. If it is a quarter of the ring, if we are taking only a quarter of the ring and a current I is passing through here, how much will be the magnetic field here? It is equal to B equal to mu 0 I by 4 pi r into phi, which is equal to mu 0 I by 4 pi r. Quarter means how much is the angle here? This is 90 degree. It is 90 degree. So it's 90 means pi by 2. So pi and pi gets cancelled. How much is the result? Mu 0 I by 4 into 2 is 8. 8r. So this is the expression. This is how we finding a magnetic field due to a circular current. Okay. The direction of B. So let's see how the direction of magnetic field. We know how to find the magnitude, but we need to find the direction also. So first we consider the linear currents. Here we are considering linear currents. If this is the first case and if a current I is passing through this straight current carrying conductor, and we need to find the magnetic field here. At this point we need to find the magnetic field. We don't know how the magnetic field will be. It will maybe into this page, as if you are considering this page, and this is a straight current carrying conductor that we have placed in this page, and magnetic field may be into this page or out of this page, we don't know. So into this page or into this plane is represented like this, and if it is out of this plane it is represented like this. So we are considering the right hand thumb rule. You take your right hand and just curl like this. So this is the current carrying conductor. You can see this current carrying conductor here. So we are placing our right hand here and curling our fingers like this. So if this is the direction of current, if this thumb is the direction of current, then this curled fingers will direct the direction of magnetic field. That is, the magnetic field will be around this around this straight current carrying wire. So this is the direction of magnetic field. How this circle goes, that is the direction of magnetic field. So if we want to find the magnetic field here, so you know this magnetic field is coming like this and it is going into this plane. Okay, so at this point if we are finding the magnetic field, it is into this plane. As we are considering a 2D image, this is into this plane. So this, at this point it will be into the plane, so it can be represented as like this, into the plane. At this point the magnetic field is into this plane. So just take your right hand and just curl like this. So the similar case, if it is opposite, and if this is the current I, this is passing through this direction, downward direction. So how you need to find the magnetic field? You take your right hand and curl like this. This finger shows the direction of current. Always place your finger in the direction of the current. This thumb finger. Okay. So it is in this direction of current. So how this other fingers are curled like this direction. Okay, so this is the direction of magnetic field. So if we need to find the magnetic field here, which means it is outward, as you coming the magnetic field coming from this side to this side, back side to front side. So it can be represented like this. This is the magnetic field here, outward the paper or outward the plane. And if you are finding the magnetic field here, you just consider this is inward, that is magnetic field lines are going into this plane. So this is the magnetic field here. As we know, the magnetic field is around this straight current carrying conductor and it is a 3D image. consider it as a 3D image. So if we are finding on this paper at this point, only at this point it will be inward. That is why we are placing like this. We are representing like this. And at this point it is outward. That is why we are representing like this. Okay, is it clear now? Considering the circular current, let's consider the circular current here. This is a current carrying conductor which carries a current in this direction. This is the current flowing through this circular current carrier, and consider this is in clockwise direction. So if it is a clockwise direction, if the current flows in clockwise direction, the produced magnetic field inside this circle, inside this circular current will be into this plane. Okay, into the plane. So if it is clockwise, it's considered like that. If it is clockwise, if the current flows go clockwise, then the magnetic field is inward. Magnetic field is inward or into the plane. And if the current flows in anti-clockwise direction, this is anti-clockwise direction. The current flows in anti-clockwise direction. If the current flows in anti-clockwise direction, anti-clockwise or counterclockwise direction, then the magnetic field produced will be outward the plane. It is outward. Anti-clockwise means outward. Outward is represent. We know outward is represented like this, and it is into the plane. It is out of the plane. So the magnetic field created is like this here. Here it is. If it is clockwise, it is inward. Okay. So if it is clockwise, it is into the plane, and if it is anti-clockwise, it is outward or out of the plane. Okay, so we can consider the same situation what we have explained before, that is linear current also in terms of clockwise and anti-clockwise. That is, if there is a current like this, it is a straight current carrying conductor, and this is the current I. As we know, we can use the right hand thumb rule, but if this is the point where we need to find the magnetic field, then just consider this is a straight current carrying conductor, and this is the direction of current flow. Just go with this direction and come to this point. So it is clockwise like this. Okay, so when we are going with the current and coming to this point, it is clockwise, no? So we can tell that as it is clockwise, here is magnetic field into the plane. Okay, and if you are considering a straight current carrying conductor like this, is the direction of current flow, and if this is the point where we need to find the magnetic field, and we are going with the current and coming to this field, sorry, coming to this point. So how it is? It is anti-clockwise direction. Anti-clockwise direction. So here it will be outward. So we can consider the straight current carrying conductor also by using this clockwise and anti-clockwise manner. Okay, so we are considering another straight current carrying conductor I, carrying conductor which carries a current I, and if we are finding a magnetic field here at the straight, the point just outward, just here, that is this straight to this current carrying conductor. Okay, there is no, it is not up in above this line, or it is not below the line. It's just the straight point here. Here this point P, we need to find the magnetic field. Then the magnetic field at B, at P will be equal to 0. Okay, it is in the direction of the current flow. The point is in the direction of the current flow, so magnetic field will be equal to 0 at this point. Okay, just remember that point also. Coming to the few examples, then here we are having some applications, examples or applications we are considering here. Here we are having a straight wire, then a half circle like this, and again a straight wire. So here we need to find the magnetic field in this point. So considering a current flowing in this direction and this direction here, coming here, then this direction, this is the direction of current flow here. Okay, this is the direction of current flow. We are going to find the magnetic field at this point, and this is r is the radius of this half circle, semicircle. Okay, so we're just taking as three parts here. First part, this is the first part. Here we are having a straight conductor, so this is the first part, and second part we are having a semicircle, means half semicircular current carrying conductor. Then again third position we are having straight current carrying conductor. So when we are considering this point P, from this straight current carrying conductor. This is in line with this straight current carrying conductor. Okay, this is in line with this straight line like this. So due to this current I, the magnetic field will be zero here, as we just said before. Due to this current, due to this first portion of the current carrying conductor, there will not be any magnetic field as it is in line with this carrying conductor, current carrying conductor. So due to the first portion, there will be no any magnetic field. So first portion, due to first portion, it will be zero. Similar here also. Here also the current going in this direction, but even though this in a single straight line. Okay, so B third portion, due to third portion also there will be a magnetic field zero. So we need to find only the magnetic field due to this second portion. Okay, second portion means it is a semicircular portion. So as you know, the magnetic field produced will be, we are having an expression that is mu 0 I divided by 4 pi r into that angle. So this is the expression that we know. So it is equal to mu 0 I divided by 4 pi r into what is this angle? The angle which makes with this point. Okay, angle of this total semicircular or this circular portion or semicircular portion making with this point. So it is, as we know, this is 180 degree. So this is pi only. So pi and pi gets cancelled. So which is equal to mu 0 I divided by 4r. This is the expression. And also we need to find the direction. So this is in clockwise direction. As you know, if the current flows in clockwise direction, the direction of magnetic field will be always into the field. So this is the magnitude of this field and this is the direction. Okay. So this is the second example. Here also we are having a current I passing, coming from here, current I, and then it is going through this position, and then it is passing through here. So these are the three positions, three directions of current here, and we are finding the magnetic field at the point P here, which makes a radius P. It's having a radius R while considering the circle, semicircle, and also here we can divide this in three parts. So this straight portion is the first portion, and this semicircular portion is the second portion, and this straight portion is the third portion. We can consider as three portions. So first we are considering the first portion. But, due to the first portion, there is a magnetic field at P. So first we need to find the distance. This distance, this is equal to r, as this is the radius of the semicircle. This is also equal to r, as this is given as r. So while considering the straight line with respect to this point P, this is like the conductor is infinite at one end, like infinite at one end. Okay, and this is the point where we need to find the magnetic field. So due to the first portion B first will be equal to, this is the case we have already studied, and the expression we know, mu 0 I divided by 4 pi r, infinite at straight current conductor, infinite at one end. Okay, so this is the expression, and we do need to find the magnetic field direction. Here you just take it like this. So this is the direction of current, this is the current direction, and we are coming to this P. We are just coming with this I, the direction, and coming to this P. It is like a clockwise direction. Okay, it is like clockwise. So if it is clockwise, then the magnetic field will be into the plane. Okay, so this is the first, it's the magnetic field due to the first position. And coming to the third position again, third position or third part, B third will be equal to, it is also same, similar condition here. So mu 0 I divided by 4 pi r, here also 4 pi r, and the direction we need to consider. So this is the direction of magnetic current here, direction in this direction. So P, coming to this P here, uh, in that is we are going with the direction and coming to this point P. So this is also in clockwise direction. Okay, while going with this current direction I, coming to this P will be, that is also in clockwise direction. So this is also in clockwise direction. Both are in same direction magnetic field. And next we need to find the magnetic field due to the second portion, that is mu 0 I divided by 4 pi r into the angle, which is equal to mu 0 I divided by 4 pi r. What is angle here? This is also semicircle, half circle. So the phi will be, that angle will be equal to pi, 180 degree pi. So this pi and pi gets cancelled. Mu 0 I divided by 4r, and this is in which direction? Anti-clockwise direction. The current direction is anti-clockwise. So the magnetic field is out of the plane. So these are the three magnetic fields due to these three different current carrying conductors. So what will be the total effect? Total effect will be the sum of all these three. Okay, so sum means this first portion and second portion are in same direction, and third portion in opposite direction. So what we can do is, we're just taking as like taking adding these two and subtracting another one, or taking this one and subtracting these two. Okay, so first we need to consider like mu 0 I by 4r, and this is mu 0 I by 4 pi r. So maybe this will be the highest in magnitude. So first what we are doing is b total is equal to b second portion minus b first portion minus b third portion. Okay, third portion. And as this, we consider this one as first, this is the direction outward the plane. Okay, so this is the magnetic field that we are finding, that is b second portion means mu 0 I by 4 r minus, this is the b first one, that is mu 0 I by 4 pi r, again minus mu 0 I by 4 pi r. Okay, which is equal to mu 0 I divided by 4 pi r can be taken outside. 4 pi r, here there is no pi, so we need to multiply by using pi. So pi minus here 1, here 1, that is equal to mu 0 I divided by 4 pi r into pi minus 2, which is the direction, outward direction. So this is the total magnetic field due to this current carrying conductors. Okay, so what we are doing is just taking different parts separately and take the sum. Here coming to the third example here. Third example, here the current is coming like this, then this direction, then again this direction. Okay, so here we need to find the magnetic field at P. So this is having distance r here and also r here. So this is the first position, first part, this is the second part, and this is the third part. Okay, so due to the first position, first part, b first will be equal to magnetic field due to the first position, this straight current carrying conductor. This is its infinite at one end, straight current carrying conductor compared to this point P. So mu 0 I divided by 4 pi r, and this is in like clockwise, so into the plane. Again P third portion also, third portion. Third portion means here the current flowing in this direction. Okay, this direction. So coming to this direction and going to this point P means it is in anti-clockwise direction. Okay, it is in anti-clockwise. So the magnitude is same, mu 0 I by 4 pi r, but anti-clockwise direction. Okay, then second portion, second portion will be equal to mu 0 I by 4 pi r into that angle. Angle is pi, half circle, so pi only, which is equal to mu 0 I by 4r into, this is in this direction. So this is the direction, as this is the direction clockwise, sorry, anti-clockwise direction. So out of the plane. Okay, so what will be the total effect? B total will be equal to, B total will be equal to, so first we are considering the outward direction that we are considering. So mu 0 I by 4r, mu 0 I by 4r minus, sorry, not minus, here also one more same direction magnitude is there, plus The third one, mu 0 I by 4 pi r, then minus another direction is there, mu 0 I by 4 pi r. Okay, so this is the net magnetic field, and first we have taken outward direction, so this is outward only. These two will get cancelled, so the resultant will be mu 0 I by 4 r into outward direction. Okay, coming to another example, here we have a current going like this, like this, like this, and this. So this is the directions of current flow. So here we can consider this as does 4 parts. This is the first position, this is the second portion, this is the third portion, and this is the fourth portion. So dividing this uh, current carrying conductor as 4 parts, we need to find the magnetic field here. This is given, the radius is r1 and this is radius r2. Okay, so how we will find, first we can consider these two portions, the second portion and fourth portion, as both these portions are in line with this point, these two portions will produce a zero magnetic field at this point. Okay, so the magnetic field due to second portion as well as the magnetic field due to the fourth portion will be equal to 0. Okay, next we need to consider the field due to the first portion b1, that is equal to mu 0 I divided by 4 pi r. What is r here? This is r1, first portion, so this is r1, radius is r1, into the angle phi. What is angle phi? This is also semicircle, half circle, so the uh, angle is pi only, pi, which is equal to mu 0 I by 4 r1. Okay, what is the direction? This is in this direction, so this is anti-clockwise direction compared to this point P. This is an anti-clockwise, so there is an, as it is anti-clockwise, it is out of the plane. Okay, and considering the third portion, the small semicircle, so here also mu 0 I divided by 4 pi r. R means here r2, this is the radius r2, into the angle is same, as it is also a semicircle, half circle, it is pi only. So this gets cancelled, mu 0 I divided by 4 r2, and what is the direction here? This is the current direction, so this is clockwise direction, so it will be producing a magnetic field into the plane here, so into the plane. Okay, so we can consider any position, any point, b3 or b1 first. Like that we need to consider the direction also. First we are considering the b3, so b total will be equal to b third portion minus b first portion. As we have taken the b third portion here, it is in clockwise direction, and subtracting the another term, so this is in clockwise, taken it as clockwise, which is equal to mu 0 I divided by 4 r2 minus mu 0 I divided by 4 r1 into clockwise direction, which is equal to mu 0 I divided by 4 into 1 by 1 by r2 minus 1 by r1 in clockwise direction. Okay, we come to another example. I have just plotted like this. So consider this is the current I that started flowing from here, then coming to this position here, like this, like this, like this. So this way, this way, this way, and coming to this here P. And P we need to find the magnetic field. Okay. So as you know, even though we are having a current flow in this direction, these directions, this side directions, here also this direction and this direction, all these portions will produce a zero magnetic field at P, as it is in line with the point P. Okay, as it is in line with this point P, so we need not to consider those points, we those portions. We need to consider only the position here. This is the first portion, this is the second portion, this is the third portion, and this is the fourth portion that we need to consider. Okay, so due to the first position portion, B1 magnetic field will be equal to, this is like a portion of a circle which is having an angle theta with this point P. This all these portions will make an angle theta with this point P. Okay, so first portion, due to the first portion, it will be mu 0 I divided by 4 pi r into the angle theta, 4 pi r into the angle theta, and direction we need to consider. So here, what is the r? Radius will change. It is not actually it is not r. What is a radius here? First, this portion is here. Here we have given r, r, r. All these portions are r only. So here first r is there, second one is there, third one is there, fourth one is there. So it is 4r. It is not simply r. This is 4r into theta. And what is the direction? As it is in clockwise direction, it is into the field. Okay, so mu 0 I divided by 4 pi into 4r into theta and into the field. Okay, so due to the second portion, which is equal to mu 0 I divided by 4 pi into, it is also making an angle theta. Theta is same theta. And what is the radius here? R, R, R. So on the second portion we are having 3R. So 3R into, what is the direction of magnetic field? This is in anti-clockwise direction, so out of the plane. Okay, and due to the third portion, mu 0 I divided by 4 pi, only 2R. First R and second R. So 2R is the radius into theta, and this is in clockwise direction, so into the field. Again, due to the fourth portion, mu 0 I divided by 4 pi, this is r only r is the radius, r into theta. What is the direction? As this is in anti-clockwise direction, this is out of the plane. Okay, so what will be the total final expression for magnetic field? B total is equal to sum of all these things. Okay, so first one, we can consider the first one. This is the B1, like this, B1, B1. I will just write like that only, B1, and this is in opposite direction. This is into the plane, this is out of the plane. So minus B2, again this is in same direction. So plus B3, then this is in opposite direction. So minus B4, which is equal to mu 0 I by 4 pi is common in all these things, and theta is also common. Okay, theta is common, and r is also common. All these things, r is also common. Into, in first one, what is remaining? 1 by 4 is remaining. Here 4 only remaining. So that is 1 by 4 minus, in second expression, what is remaining? 1 by 3 is remaining. 1 by 3 plus, in third expression, 1 by 2. In fourth expression, 1 only. Okay, so what is the expression that we are getting here? What is the direction will come? As first one we have taken into the plane, and that is taken as positive, so into the plane is the direction here. So which is equal to mu 0 I divided by 4 pi r into theta. And what is the total? When we are solving this expression, we are getting minus 7 by 12. So into minus 7 by 12. Okay, minus 7 by 12 we are getting, which means in, what is the direction? Into the field, which means mu 0 I by 4 pi r into theta into 7 by 12. This is the total magnitude, and here is a minus sign, and this is the field direction into the plane, and minus sign, which means out of the plane. That is, this is the direction, and it is just opposite to this direction, which means here we are not considering this minus sign here, and just making the direction opposite out of the plane. So this is the final expression that we are getting. Okay.